Okay, good morning to all. Today we see the numericals on the tower design of fluid-fluid reaction. Okay, so some numericals we'll see in this lecture, and some numericals we'll see in the next lecture. Okay, now in the previous lecture we have seen the design of the tower. Okay, absorption column. Okay, how this to determine the height of the tower with straight mass transfer and mass transfer as well as chemical reaction. Okay, there are two different types. Okay, in the design of the tower. Okay, so straight mass transfer alone only, that is the absorption. Okay, and already you have studied in the mass transfer. Okay, now here in the heterogeneous type of the reaction, fluid reaction, gas liquid reaction. Okay, in the separation process, this heterogeneous reaction be occur. Okay, in a liquid regime. Okay, and this liquid regimes, reaction regimes, kinetic regimes, already we are seeing. Okay, now here we'll see the numericals. First we see the numerical on the absorption tower. Okay, the concentration of undesirable impurity in air, that is a 1 bar. Okay, impurities in the air is given 1 bar, is to be reduced from 0.1% to 0.02%. Okay, pressure is given 1 bar and concentration is reduced from 0.1% to 0.02% by absorption in pure water. Okay, determine the height of tower required for countercurrent operation. Now from this problem, you must be identify which type of this tower is there. It is only straight mass transfer or it is a mass transfer with chemical reaction. Okay, so here water is using as a liquid. Okay, and this liquid means that is the solvent, and these impurities are, this water is coming contact with the air, and these impurities from the air is dissolved in the water. What is this? There is a no chemical reaction, only it is the pure water is there. Means water is not a reactive liquid. What is this? So there is a no chemical reaction, only straight mass transfer is occur in this process. Okay, straight mass transfer is occur in this process. Okay, means there is a not a B, means A plus B to give the product. This is the reaction, which will be not a happen here. Okay, only remember this thing. Okay, only straight mass transfer is there. Impurities are added in the water. Okay, so remember, when water is pure water is there, means there is a no reactant. Okay, means only straight mass transfer is occur. Okay, remember this. And this impurities concentration is reduced from 0.1% to 0.02%. So data is given Kag is equal to 0.32 mole per hour per meter cube per Pascal. That is the mass transfer coefficient in gas stream. Then Kal, which is equal to 0.1 per hour. Okay, mass transfer coefficient in liquid film. Ha is the Henry's constant, 12.5 Pascal meter cube per mole. Flow rates are given for the gas Fg upon ACS. ACS means that is the cross section area of the column. Fg upon ACS, which is equal to 1 into 10 raised to 5 mole per hour per meter square. Fl upon ACC, ACS equal to 7 into 10 raised to 5 mole per hour per meter square. This is for gas, this is for liquid. Liquid flow rates are given. Total molar density of liquid is 56,000 mole per meter cube. This is the given. Okay, so this data is given. From this data, we use this calculate the height of the tower. Okay, so we'll see the solution, how to solve. Okay, so this is the tower. Okay, then input, suppose consider here 1, 2. Okay, first, then what is the PA1? PA1 means how to calculate the P1, PA1. Okay. PA1, how to calculate? Okay, so see, this is 0.1 PA1, and this is the output of the gas. Gas is entered from the bottom, that is the PA2. Okay, and this liquid is entered. This inlet is the CA1 at 0.1, and output we get at 0.2, that is the CA2. Okay, now what are the given in the problem? First, okay, there is a one total pressure is given, that is the 1 bar. 1 bar means that is the 10 raised to 5 Pascal. 10 raised to 5 Pascal. Okay. Then this partial pressure of this impurity, where impurity concentration or partial pressure you need to calculate. So impurities partial pressure, how we calculate? Partial by using Dalton's law. Partial pressure is equal to mole fraction in the gas phase multiplied by total pressure. Total pressure is the 10 raised to 5 Pascal and multiply by mole fraction. Mole fraction at inlet, how much in the problem? It is given 0.1% to 0.02%. Mole fraction is 0.1%. This fraction is the 0.1 divided by 100. Divided by 100 means 0.001%. 0.001%. So 0.001 multiply by 10 raised to 5. Multiply by 10 raised to 5. So here 100 Pascal we get it. Same way, this is reduced to the 0.02%, means 0.02 divided by 100. 0.02 divided by 100. This is the mole fraction of impurities at outlet in the year. Okay, so 0.0002. Okay, multiply by 10 raised to 5 total pressure, that is the partial pressure of the impurities at the outlet. So PA1 is equal to 20 Pascal. What is this? So this we get PA1 and PA2. Then what is the CA1? CA1 means that is the concentration of A. A means that is the impurity. Okay, solute. So this is the pure water, and in the pure water initially there is a no impurity. So CA1 is equal to 0. Okay, initially CA1 is equal to 0. So output, this is not given in the problem. So CA2 you must be calculated by using material balance equation. Okay, so material balance equation, what is material balance input is equal to output, and in the derivation already we have seen. So G upon pi. Okay, so G upon pi into PA2 plus L upon CT into CA1, which is equal to this, the input, output is G upon pi into PA1 plus L upon CT into CA2. Our equation, all of you know, G upon pi into dPA, which is equal to L upon CT into dCA. This equation in terms of A, not a B. Remember, this is a pure water. Okay, only straight mass transfer is occur. So design of straight mass transfer. Okay, this design of the tower with straight mass transfer alone. Okay, so this derivation we use it, equation we use it here. Okay, so from this equation we rearrange this J upon pi into PA2 minus PA1, which is equal to L upon CT into CA2 minus CA1. Okay, and use this equation. What is G? G is given in the problem. Data is given. Okay, so this data, all of you know. What is G? G is the 1 into 10 raised to 5 mole per hour per meter square. L is the this 7 into 10 raised to 5 mole per hour per meter square. Okay, CT means molar density, that is the CT, mole per meter cube. Okay, that is the total concentration, 56,000 mole per meter cube. This is the mass transfer coefficient in gas stream, this mass transfer coefficient in liquid stream, and HA, this value is given here. Okay, pi means that is the total pressure, and this is the 1 bar is given. Okay, and put all these value here, calculate CA2, and which is equal to 6.4 mole per meter cube. After solution, we get the CA2 is equal to 6.4 mole per meter cube. Okay, then using the equation of H, height of the tower, how we calculate the height? H is equal to G upon pi into KAGA integration from PA1 to PA2 dPA upon PA minus PAI. Okay, so this is the equation. So, okay, so this equation is the H is equal to G upon pi KAG into PA. Okay, so this integration from PA1 to PA2 dPA upon PA minus PAI. Okay, now H, G, you know it, 1 into 10 raised to 5, pi, you know it, total pressure 10 raised to 5, KAGAI. Okay, now this KAGA we need to calculate it. Integration from PA1 to PA2, PA1 you know it, okay, and PA2. Okay, so this from PA1 is the 20 and PA2 is 100. Integration dP upon PA minus PI. Now PA minus PI, partial pressure in the bulk of the gas, and PI is the partial pressure of impurity at the interface. Okay, gas stream and liquid stream interface. So how we calculate this PAR? Okay, PAI. Okay, so using the equation. Now first of all, this KAGA. Now this KAGA. Remember this in the problem given KAGA. Okay, here this KAG and this KAL. Okay, it is a given here. That is the individual mass transfer coefficient. Individual mass transfer coefficient. Now calculate here overall mass transfer coefficient. Okay, why need to calculate here overall mass transfer coefficient? Okay, you remember this concept. PA minus, this is here PA minus PAR. PI, we are not able to calculate the PAR. Okay, so we calculate the PA star here. PA star means what? This is also the partial pressure of A at the interface, but it is a equilibrium with the CA. Equilibrium with the CA. This PA is equilibrium with the CA. Correct? It means that is the PA which is equal to HA into CA. So bulk concentration of A is, okay, we know it. Bulk concentration of A in the means bulk concentration, that is the impurities concentration in the bulk of the liquid or bulk of the water, we know it. Hence we use the here PA minus PAR. Okay, instead of this PA star we take, and when we use the PA star, okay, and it is equilibrium with the bulk of the liquid, then we use a overall mass transfer coefficient. Then we use the overall mass transfer coefficient. Okay, if it is not a equilibrium, if we know the PI value, then we use the individual mass transfer coefficient here, KAG. Okay, means you must be know this concept. Okay, means we have solved the how to calculate the overall mass transfer coefficient. This equation you know it, how to derive in interface mass transfer. We are using there PA and PA star. This PA minus PI, this difference is very less. Hence we consider the PA star, and this PA star is a PA star is a equilibrium with the constant bulk concentration. Okay, so we use this equation. So use the equation PI is equal to HA into CI. It is a equilibrium. Instead of this PA star, we write the PI. PI is equal to HA into CI. Okay, so this PA star is equal to HA into CAL. L means that is the bulk liquid concentration. Okay, so this overall mass transfer coefficient we calculate by using this equation for the gas stream. Okay, so 1 upon KAG, which is equal to 1 upon KGA, individual mass transfer coefficient. Okay, plus HA upon KL, which is equal to 1 upon this, we know this KAG is given 0.32 plus this HA is given 12.5 upon KL is given 0.1. In the data is this value is given. So we calculate 1 upon KAG, that is 128.125. Okay, so take the inverse of this. So KAGA we obtain, which is equal to 0.0078 mole per hour per meter cube per pascal. Okay, so this PAI, which is equal to HA into CI. Okay, now this difference PA minus PI, check the difference in the column from bottom to top or top to bottom. It is a constant or different. Okay, so how to check? So make one table. In that, take the first PA value, then correspondence CA value. Okay, then for this equilibrium, we calculate the PAI. PI is equal to HA into CI, this C. Okay, CA. So then calculate PA minus PI in the column. Okay, now at the top of the column, at point 1, at the top of the column, this, okay, in this top of the column. So what is PA value? 20. What is correspondence CA value? 0. Okay, here 20, 0. What is the PA, which is equal to HA into CI? PI is the CAI is the 0, HA is the 12.5, CI is the 0 here. So PAI is the also 0. So what is the P minus PI? This difference P minus PI is the 20 minus 0 is the 20. This at point 2. Now we check at point, suppose in the column middle point we take. Okay, so middle point, or first we check at the bottom of the column. So at the bottom of the column at point 2, it is the PA is the 100 here. Okay, here 100 is there. What is CA2? We calculate 6.4 here. Okay, so we take this 100, CA is 6.4. PI we calculate HA into CI means 12.5 into 6.4. We get the 80. So 100 minus 80, that is the 20. Okay, now check at the, suppose 20 this constant we get at the top and bottom. Now at the middle of the column, it is the difference or it is a constant. Okay, we check it. So we will take the average of this 20 and 100. Okay, that is the 60. So at the middle of the column, we take the at point 3. Suppose at any point in the tower, we take the average, that is the PA is the 60. Similar way, using this at the top or bottom section. Okay, at the top or bottom section, we take the material balance. Same equation we use here. Instead of this, suppose at the top, PA1, we know the 20. Now PA3, we calculate, take the average, that is the 60. So at 60, what is the CA? We calculate. So using this material balance, J upon pi into, suppose PA3 minus PA1 is equal to L upon CT into CA3 minus CA1. So CA3 we calculate. Okay. So PA1, you know it, 20. Okay. CA1, you know it, that is the 0. So PA3 is the 60, and so CA correspondence CA3 we calculate, we get the 3.2. We get 3.2. Okay, so 3.2 multiplied by 12.5, so we get the PI is the 40. So 60 minus 40, this difference is the 20. Means what? What is meaning of this? Okay, this PA minus PAI, this value, this difference is the constant from top to bottom of the column. Okay, means this PA minus PI in this equation, in this integration, PA minus PI is a constant, that is the 20. So we put this value. So H is equal to, we put the value, G is the 1 into 10 raised to 5 upon pi is the 10 raised to 5. Okay, this KGA, the 0.0078 we calculate here. Okay, overall mass transfer coefficient in the gas phase. Integration from PA1 is the 20 to PA2 is the 100. Okay, dPA upon 20, dPA upon PA minus PI, this is the constant, is the 20. And so dPA is the 100 minus 20, that is the integration. Solve this, and H is equal to 512.5 meters. This is the height of the tower. Okay, so this is the solution. Now remember this, only here, this overall need to calculate the overall mass transfer coefficient for straight mass transfer is there. Okay, for remaining problems, other problems, mass transfer with chemical reaction, there is, we use the individual mass transfer coefficient. But here, remember, to need to calculate the overall mass transfer coefficient and this equation, difference PA minus PI, this difference. Okay, so this is the procedure to calculate the height of the tower. Okay, now another example we see. We plan to remove about 80% of the A present in a gas. Okay, 80% of A present in a gas stream by absorption in water containing reactant B. Okay, material B react with A as per the following gas. So this is the absorption, problem is the absorption with chemical reaction, and this reaction is given A plus B to give the R. A is the gas, B is the liquid. Reaction is extremely rapid. Extremely rapid means instantaneous reaction we consider. This type of reaction is given. So use the equation of the instantaneous reaction, case A and B. Okay, so determine the height of the tower for counter current operation using following data. G is given 1 into 10 raised to 5 mole per hour per meter square. Pi is the 10 raised to 5 Pascal. Air is given 7 into 10 raised to 5 mole per hour per meter square. Okay, HA is the 12.5 is given. CT is equal to 56,000 mole per meter cube. If density is given, then convert it into the CT. Okay, CT is equal to 56,000 mole per meter cube. PA in is given 100 Pascal. KAGA is the 0.32 mole per hour per meter cube Pascal. Okay, KGA given. KLA is given 0.1 per hour. Concentration CBM. Okay, this liquid concentration CB is given. Concentration of reactant B in the water entering the tower is 800 mole per meter cube. Assume that diffusivities of A and B in the water are the same. Okay, so DL and DBL, these are the equal. Okay, so this problem is given. Means here 80% of A is present in the gas. concentration of partial pressure of A in is given 100 Pascal. Okay. So, and total pressure is given 10 raised to 5 Pascal. Okay. So, calculate the output concentration. Also, CBN is given 800 mole per meter cube. So, calculate CB means bottom concentration of liquid. Okay. Now, this is the tower. Okay. This is the given. So, PA2. So, here input is given 100 Pascal. Okay. So, what is the output? The output is the now 80% is want to remove. Means how much remain is there? 20%. 20%. 20% means 20%. 20 divided by 100 into 10 raised to total pressure is the okay. We want to remove. So input is the 100 Pascal. So what is remaining? 20%. 20% of this 100 Pascal. 20% of 100 Pascal. Okay. So 20 means 20 Pascal will be there. So output is the PA1 is the 20 Pascal. Now input is the CB1. It is given 800 mole per meter cube. Now we are not, you are not using A, CA. We are using the CB because A and B are liquid reactant reacted each other. Okay. So this PA2, PA1 similar way. CB1 is the 800 mole per meter cube. Output is the CB2. So this is given. So material balance equation we use here. Okay. So what is the material balance equation? For the now use the derivation of the design of tower for mass transfer with chemical reaction. So this material balance equation, input is equal to output G upon pi into delta PA or dPA, which is equal to, this is counter current operation, minus L upon B into CT into delta CB or DCB. Okay. So G upon pi into PA1 minus PA2, which is equal to minus L upon B into CT into CB1 minus CB2, or PA2 minus PA1 we can write, or CB2 minus CB1. Whatever you write PA2 minus PA1, you should be right here CB2 minus CB1. Okay. So like this. Then put the values. What is G is given in the problem, 1 into 10 raised to 5. What is L? 7 into 10 raised to 5. Pi is the 10 raised to 5. B is the stoichiometric coefficient of the reaction. Reaction is A plus B to give the R. So stoichiometric coefficient of the B, okay, of the liquid in the reaction. So this B is equal to 1. Okay. So reaction B is equal to 1. So this stoichiometric equation in that this B is equal to 1 here. So LCT is the 56,000. We know it. So what is PA1? That is the 20. PA2 is the 100. Okay. What is CB1? It is the 800. Calculate the CB2. And by after putting the value and after solving this equation, we get the CB2 is equal to 793.6 mole per meter cube. Remember, this CB2 must be decreased less than CB1. Okay, here CB is react with the A, means some B is consumed. So CB2 is the 793.6 mole per meter cube. Okay. Now this is the instantaneous type of reaction. Now instantaneous type of reaction will be occur in the liquid phase. But this reaction is controlled by the gas film or liquid film. There are the two cases we have seen: gas film control reaction and liquid film control reaction. So this we need to case 1 and case 2 already we are discussed in the kinetic regimes. So how to check this? So this condition. Okay. First of all, we calculate this CB2, input and output condition of the tower. We know it. Okay. Now at the top of the tower, we check the condition. Okay. What is the condition? We check this condition. Which condition we check? KAGA into PA is less than or equal to KL into CB. KLA into CB upon B. B is equal to 1. Okay. So we are not right here. So KG into PA. If it is less than or equal to KG into CB upon B, then gas phase is resistance control. If KG into PA is greater than KLA into CB upon B, then it is the liquid phase is resistance control and CB is high. Okay. But now check it. At the top of the tower, KAG into PA. This value. KAGA into PA. Okay. What is KAGA? That is the 0.32. We know it. What is the PA at the top of the tower? 20 Pascal. So this 0.32 into 20 is the 6.4. What is the KLA? This is the 0.1. This in the data is given. What is CB? CB1 at the top, this is the 800. So 80. So from this what we get, okay, 6.4, okay, kg into Pa, which is the less than this 80, means Cb is high. So this reaction at the top, gas phase resistance control. Now check at the bottom of the tower. Similar condition, kj into Pa at the bottom, 0.32. At the bottom, Pa is the 100, so it is the 32. KLA is the 0.1, and what is CB at the bottom? We are determined 793.6. So that is the this product KLA into CB. Now again we check here. This 32 is less than this 79, means kg into Pa. Again here less than KLA into CB, means at the top and at the bottom, both sides kj into Pa is less than or equal to KLA into CB. So CB is a high at the top and at the bottom of the column, means here gas phase is resistance control. So gas film is a resistance control step for determining the rate of reaction. So what is the rate of reaction for the gas film resistance control for instantaneous or fast reaction? Minus Ra is equal to Kj into Pa. Simple equation. Kaj into Pa. Okay. So Kj is the 0.32 into Pa. Okay. So partial pressure is vary from top to bottom of the column. Yes. So rate of reaction minus Ra is equal to 0.32 into Pa. Use this rate of reaction equation, rate equation. So this rate equation we use here. So calculate the height of the tower. H is equal to G upon pi integration from Pa1 to Pa2 dpa upon minus Ra. We know this equation. Okay, we know the equation. H is equal to G upon pi integration from Pa1 to Pa2 dpa upon minus R. So what is Pa1? It is the 20. What is the Pa2? It is the 100. Okay, so this G, we know it 10 raised to 5, pi is also 10 raised to 5. Integration, G means 1 into 10, input gas rate. Integration from Pa1 to Pa2 is the 20 to 100. Okay, then Pa dPa upon minus Ra we calculate it 0.32 into Pa. Okay, so we take the integration of these 10 raised to 5 cancel, dPa 1 upon 0.32 we take common, dPa upon PA, that is the ln of 100 upon 20. Ln of PA means ln of, put the limit, ln of 100 upon 20. Solve it. So H is equal to 5.03 meter. Okay, so this is the height of the tower. Now here, see, this is the important thing. This is the previous problem is the only straight mass transfer. Now this problem is for the mass transfer with chemical reaction. Now with chemical reaction means reactant B is there, concentration is given. Then you this equation, so conditions you use, that is the check the condition, that is the gas film resistance control or liquid film resistance control. Okay, at the top and at bottom both sides you check it. At the top, suppose gas film is resistance control, at the bottom it is the gas film resistance control, then use the same equation, minus R is equal to Kg into Pa, this rate of reaction, and H is the J upon pi integration P1 to P upon minus Ra. So this is the height of the tower. This is the common equation for the for all the problem for calculating the height of the tower for mass transfer with chemical reaction. Okay. So in the previous problem only straight mass transfer. So another equation is there. Okay. Now here this minus Ra here given this here. Okay. Put these values and solve this equation. We get the, if it is the in the sum problem, okay, these conditions at the top and at the bottom. At the top, suppose gas film is resistance control, and at the bottom this condition is reverse. Suppose Kg into K is greater than KL into Cb. Okay, then what happened? At the bottom there is a liquid film is resistance control, and at the top there is a gas film is resistance control. So in the tower there are two films, two regions are formed. At the top region, suppose gas film resistance control, and at the bottom regions liquid film resistance control. Okay, so this region, so we need to calculate where the gas film resistance end and where the liquid film resistance control start. This point we need to calculate in the tower. Okay, then at the top we take the different equation, at the bottom we take the different equation of the rate of reaction. Okay, So then we calculate at the top h1 and at the bottom h2 and take the summation, that is the total height of the tower. So this is the procedure for calculating. Okay, so we see in the next lecture. Okay, for these different conditions. Okay, so any